So there was, yesterday we started logs, which is the inverse of an exponential. If we have something like log 2 of 8 equals 3, we say it log base 2 of 8 equals 3. 3 is the exponent, and the first thing we need to do with logs is be able to go back and forth between logarithmic form and exponential form. The base is the same. The exponent and the argument are kind of different. It was John Napier was the guy who came up with them. It was in like the late 1600s as an easier way to deal with calculations, because back then they didn't have calculators, so they built tables. We did all sorts of different things. We talked about the common base for a log as 10, because, well, our whole number system in Western math is based on 10, and then we have the natural logarithm, which has a base e, which is a fundamental constant. And I'll look up where the e comes from. I'm pretty sure I know what it is. Well, that we'd already done. We wrote in logarithmic form, log base 4 of 16 equals 2. So that was some of the stuff we evaluated. There's three kind of nifty things. If we have, these are, oh, 4. Then there's another page looking at just quickly the graphs. Log base 7 of 7. Log base, whoops, log of 10. Log base 2 of 2, any of these, because I can rewrite this as 7 to what power equals 7. Well, what's x going to be in this case? Actually, I don't want that there. So log base 7 of 7 is 1. Log of 10 on your calculator is 1. Log base 2 of 2 is 1. If the base and the argument are the same, it has to be 1. What 6 to what power equals 1? Well, the only way to make an exponent equal 1 is 0. 6 to the 0 equals 1. So the log, regardless of the base, I mean, I can play with 2 on the calculator, 1 log 1 natural log, regardless of which one you do, is going to be there. Well, log base 8 of 8 is 1. Interesting. 8. Oh. So as an exponent, 8 to what power equals 8 to the 5th? What's x going to equal here? 5. Because there's actually a law of logarithms that say we can take this and move it out front, and then do log base 8 of 8 is 1 times 5. Log base 5 of 0. Log base 10 of 0. I can look at that on the calculator. Or 5 to what power equals 0? Well, the argument will never equal 0. No answer. Because you cannot take the logarithm of 0. Invalid input. Because that has no real solution. 5 to the negative gives a, like, because if we have 5 to the x, this is the, well, there's a horizontal asymptote here. X never actually becomes 0 or less. So that has no solution. So a logarithm is the inverse. So we talked about exponential function, radioactive decay, bacterial growth, population growth, continuous Compound interest. Oh, this is what happens when you steal things from people. That drives me batty as a chemistry teacher. It's lowercase p and h. Um, pH is a logarithmic scale of acidity in base 10. Something that has a low pH, like 1, is very acidic. Something that has a pH of 13 is very basic. IT, computer programming, computers run in base 2 because that's the simple, well, that's how they're all programmed. Um, it's the whole on off. Calculus, you're going to use the base E. There actually is some base E in physical chemistry and physics. The Richter scale for earthquakes is a logarithmic scale. Well, we've seen logarithmic scales recently in all these COVID cases. When you have a scale, a logarithmic scale, instead of going up by 1, well, you have 10, you have 100. That's a logarithmic scale where it's going up by an order of magnitude. Earthquakes are like that. An earthquake of magnitude 5 compared to an earthquake of magnitude 6, well, and the 6 is not 1 unit stronger, it's actually 10 times stronger than that. Sound is the same idea. Decibels is something like that. Oh, I need my pointer. Now, because you see my screen, this will be very interesting. Pop this out. Whoa. Oh, it's a TED Talk, not like the ones for a G3. I love this. Mm.
It's easy to remember log base of some number higher being the base principal the base principal of the base principal of these. Now we know logarithms are constant. We're dealing with extremely small or large numbers. Logarithms is
Well, that was interesting, but still useful. That was that. And there's another one of these slideshows, logs in math. Is that gonna? I'm not gonna go through the whole. There's only 11. What? Go away. Logarithms. We'll talk about those. Changing bases. Oh, history. This was a matter of simplifying calculations. Oh, Laplace. I, I read Napier. Henry Briggs was an old mathematician. Let's see if Napier's name shows up. Logarithmic scales, fractals. Okay, that's all good. So to quickly look at the graph, we've done y equals 3 to the x. Whoops. We can do our handy dandy -1, 0, 1. Well, that's a third, that's 1, and that's 3. So -1 and 1/3, 0 and 1, 1, 2. So that is y equals 3 to the x. We've done that. That's all perfect and fine because the log base 3 of x is the inverse of this. So 1/3 -1, 1, 0, 3, 1. Well, that's going to be 2 and 9, -2 and 1/9. So we can look at, see if we can plot some of those. So 1/3 and -1, 1 and 0, 3 and 1. So because this is an inverse and it is reflected across that line y equals x, this graph is going to look, and way over at 9 it will go up to 2, and so on and so forth. Properties: an exponential function has no x-intercept.
Mr. McKay,
Yeah.
I have a question about like what you just did up there. So I always confused. How do you know like to put like the 1/3 and then like start your
This.
x and y? I always got confused with that, and then I don't know what to do after.
So when you're doing any exponential function for your base graph, when we did trig, we did 0, 90 degrees, 180, 270, and 360. Like we did that to get a cycle,
Okay.
right? So when we do, it's like the whole key points idea. When we do exponential functions, we do -1 because it's just 1 over whatever the base is, 0 and 1, and those are going to be our, regardless of whatever the base is. We just use those as our key points because we don't really care about the whole graph. We're more interested in the shape and how it behaves kind of around the origin. Does that make sense?
I think so. So it's more. So do you always know to do -1, 0, 1, 2, like -2, and then?
Well, yeah, like we're always going to start with those. And I added that just because, like, when we do the inverse 3, 6, 7, 8, 9, so my other point would be somewhere kind of in that area. but we're just looking for the general shape of everything.
Okay. And then, so for the 1/3, did you get that from the equation, or did you? Oh, because you flipped it, or
Yeah, because 3 to the x and log base 3 of x are inverses, because this is x equals 3 to the y, and then we write it as, like, to get rid of the exponent. That's our y equals equation. So we're just interchanging the x and the y.
okay, I think that
Okay.
makes sense.
Well,
Thank you.
no problem. Colors not applicable. The y-intercept is 0 and 1. The domain was x is contained in the reals because we can have any numbers. The range is y is bigger than 0. So inverse, we're interchanging our x and our y's. So if this one has no x-intercept, if we interchange y equals log x is never going to have crossed the y-axis, because if this never crosses the x, this one's never going to cross the y. This one has a y-intercept of that, so the inverse is 1 and 0. So that point is always going to be the same. The log of 1 is always 0. The domain and the range are going to interchange. So y is contained in the reals. We can have any value for y. The domain, on the other hand, is now x is bigger than 0 because we can't cross that. This one has a horizontal asymptote at y equals oh, y equals 0. Oh, I picked a poor color. Oh, now I gotta use a different color. So for the black line, we have that as our horizontal asymptote. For the log one, well, let me get rid of, I guess I can't. Scheiße. Yeah, that's too similar. Why not? Oh, that was bad. How did, what? Silly thing. What? Oh dear. I'm sorry. This is all getting discombobulated because we've always used that. Mm-hmm. That makes a little bit more sense. We have a horizontal asymptote for the black graph, or the 3 to the x. We have a vertical asymptote for the log graph. And this one is x equals to 0. So the kind of practice stuff, so we go back to here, I'm going to write the inverse of the function, interchange x and y, write it as the logarithmic form, draw the graph of 5 to the x, because the more of this you guys do, the better. So if that's 5 to the x, the inverse of that, you're going to switch those two. And so -1, 0, 1, fill those in, flip them. 1, 2, in the same coordinate plane, use a highlighter. Rewrite in logarithmic form. So I'll do a couple of them. Rewrite in exponential form. Evaluate. This is using your kind of powers. We'll do some of them. Um, this last page that says evaluate logarithms is going to be really straightforward. So, there's an old kind of acronym, bend the log bunny. Now let's see. Log bunny. Log b to the exponent equals n. Ben, oh, I guess I've got this backwards. Can I, oh, and I didn't hear this until I started teaching. And this has nothing to do with why we named our son Ben. Base to an exponent is a number. Log base b of a number is an exponent. So if I want to write this as a log, the base is 2. The number is 10. The exponent here is x. Log base 4 of 1/16 equals -2. So as practice, the more of this you do yourself, the better. We have that right as an exponential. We have that relationship, so we're in this. 2 to the 5th equals 32. 10 to the power of 1.301 equals 20. Evaluating, determine what exponent you would need. What power do you need to raise 2 to get 8? That's a 3. What power, and some people 2 to the x equals 8. And if you write it as an exponent, some people find that easier. Some of these, log base 9 of 9. Oh no. Some of them are a little bit trickier, and I'll put answers up for those. I'll go through them later today. This is doing the graph of 10 to the x, even though 1, 2, 3, 4, 5, 6, 7, 8, I guess you may have to move that down a touch. E, rewrite in the alternate form. Well, this is an exponential. Log base 10 of 1 of 20 equals 3 are those ones. Evaluate each logarithm. I can do that one in my head. That one's 2. And that is a challenge. Calculator. I don't know what the log of 15 is. 15. Kablam. I would probably do them like trig to 3 decimal places. It's an approximation. 2, 2, 4, 8, 16, 32, 64. 2 to the 6th equals 64. 2 to the 7th equals 128. 100 is somewhere in the middle. So 6.5-ish. If you have an older sibling who will show you, I'm going to actually find the answer, but I'm not going to show you how to do it yet. The actual answer here is 6.644, but it's an approximation, so we'll show you how to do it eventually. So this is some practice. Some of them do a couple of each. It's not an assignment, but there will be questions like that on an assignment. 9. We've picked up a couple. Is there any questions before I run away?
Well, So the thing that you just did, will you put like the answers to all the solutions from the not assignment, but just like those practice questions that you gave us yesterday? Like yeah, like this stuff.
Yeah, I'll put those up later today.
Okay, thank you.
Okay. Anything else? Remember, it's a long weekend, so we won't be here on, well, Monday. Hopefully you can get out. Well, it's going to rain tomorrow, but Sunday and Monday supposedly look really nice. So hopefully we can all enjoy some nice weather. Now that I think about it, there's probably calculators on the internet that can do log of any base, but that last one where you're estimating what they are is it's a number sense thing and playing with numbers. And the more you play with the numbers, the easier this stuff gets. So that's all I have for today. I'll try to this weekend put up an assignment for um, like RF7 and RF8 and look at the rest of the stuff. But if you're doing the assignments, unless there's something horrifically wrong, it's probably just going to be like, okay, good. Because most of the mistakes that are made on assignments are mistakes that you wouldn't make if we were regularly in school, but I'll try to give some feedback. But that's all I have for today. I'll see some of you this afternoon.
Thank you.
You're welcome.
Thanks, okay.
No problem.
Thank you.
No problem. Adios.